Hello everyone, welcome back. Gustavo here. Look, today we're going to talk about PlayStation graphics, right? I know yet another YouTube video talking about PlayStation graphics, but I want to approach this topic from a different perspective, right? We're going to put our programmer's hats on, and this is going to be a programmer's technical analysis of why PlayStation graphics look the way that they do, right? I don't want to just look at them from a perspective of a gamer and just mention and show some video captures of games here on the video. I want to actually open the black box, I want to open the PlayStation console, and I want to look at the hardware, and I want to look at the programming environment and the SDK and all the functions and all the BIOS routines. So why do PlayStation graphics have all those graphical artifacts, right? And all those issues that are very characteristic of PlayStation games. So much that even modern games, right? Nowadays you have people that create games with modern engines, Unity, Unreal, they try to mimic and they try to emulate that PS1 era, right, or Sega Saturn era. So all those low poly, low resolution games that besides being low poly and low resolution, they also have some checklist of artifacts that we find in those games, right? The textures, they look a certain way, the pixels, they move a certain way. So I want to just go over and analyze a little bit step by step, looking at the limitations, the technical reason, right? From a programmer's perspective, what is the technical limitation, technical reason, hardware limitations that make PS1 games look the way that they do. Does that sound like a plan? Right. Oh, and just before we start, let me just tell you that I am going to go against everything that YouTube tells me to do in terms of ranking the algorithm, climbing positions. I don't care how long this video is going to take, right? This is something super fun. Let's just take our time, savor this moment, right? Let's just have fun and give the attention that this topic deserves, right? So I'm just going to go and take my time. I don't worry if it's going to be a long video. Let's just enjoy. Look, it's the PlayStation, right? Everyone loves the PlayStation. Why would we rush? So to start, I want to kind of give a little bit of some of the items that I think are very important whenever we are talking about PlayStation graphics, right? When I talk about all these issues, right? These graphical issues, graphical details, these limitations that the PlayStation graphics brings. So to start, I'm going to start with the one that probably all other videos already mentioned, and is something super common that you probably heard before, which is the fact that PlayStation 1 textures, they wobble, right? So you have all these wobbly textures around, you have these artifacts, this distortion of the textures. This is something that we have to talk about, so this is probably going to be the first one that we're going to cover. After that, I want to talk about something also very common, which is polygon jittering, right? Whenever you have all these PlayStation games, polygons, they jitter, right? They jump around, they always jump around the screen, so that is something that we have to talk about. What is the reason? What is the hardware limitations that make this happen, right? Why is that the way that PlayStation graphics look? Besides that, I have to talk to you about something, well, look, this is something that is very warm in my mind because I just completed the PlayStation programming course here at the school, right? So something that is very common that we usually don't think too much is the fact that we have polygon gaps, right? Sometimes, depending on how we program the game, we have these gaps in the polygons. I want to talk to you why we have something called T-junction gaps and what is this artifacts that we can see in so many games. Besides that, I want to also cover what we call lack of mipmapping in games, right? Look, sometimes these things, they are related to each other, right? Sometimes polygon jitter, they have to do with accuracy errors. Sometimes, for example, lack of Z buffer is something that is related to texture wobbliness and polygon jittering. So these things, they kind of are connected to each other. So you can look at these things almost like a table of contents of our video right here, right? So we are going to go and analyze each one of these artifacts, and we're going to explain why, giving the limitations, and look, analyzing the big reason, right? The hardware limitations or the programming limitations that actually cause these issues right here. And finally, again, something that is completely related to all of these things that I mentioned, the lack of a floating point unit coprocessor, right? So there are no floats in the PlayStation. You cannot declare a variable as a float. Well, let me rephrase that. You can declare a variable as a float, but it doesn't have hardware native support for floating point units, right? It's not a super fast floating point implementation. So I think this thing right here is basically the table of contents of what we're going to cover, right? So we have lots of things to cover. You will see that most videos, if they are talking about PlayStation graphics and PlayStation issues, they will probably focus on the first two, texture wobbliness, right? So texture affine distortion and also polygon jittering. These two are the most common ones, but I want to expand and explain really the reason why, right? I don't want to create yet another video that is incomplete. I want to go and really analyze why PS1 graphics look the way that they do, combining all of these items. And to really understand what we're talking about, we need to take a look at the hardware specifications of the PS1, right? Because just looking at the hardware, it might give us some clues of why things behave the way that they do. So let's just start with the motherboard of the PS1. So the CPU is a 33.86 megahertz 32-bit, so it's a 32-bit CPU. It's a MIP CPU provided by LSI. This is a RISC CPU, right? So this is one of the first consoles that had a RISC CPU, different than the other ones, right? The 6502s from the NES, different from the 68,000 CPUs from Mega Drive. So all these things now, we are talking about a different architecture, which is a RISC architecture. And we have only 2 megabytes of working RAM. So at a given time, we only have 2 megabytes of RAM to work with, right? So everything that we have to store, all those data structures, all those 3D objects in memory, we only have 2 megabytes. So all those games in the PlayStation, they had to work around this 2 megabyte limitation, all right? Speaking of which, we also have some chips in the motherboard which take care of video RAM. So for video RAM, we have 1 megabyte, and this video RAM, we can store inside the video RAM the actual frame buffer, meaning this mirror in memory of what is being displayed on the monitor. So we have the frame buffer that needs to be inside this 1 megabyte, but also things like texture information, right? So color of textures, all those texture images that we have to read from the CD-ROM and load, they need to be loaded inside VRAM for us to actually use them and use them in the frame buffer. All right, so this is video RAM, this is RAM, and then we talk about the GPU, right? The GPU is an SCPH 9000, which is a chip responsible for rasterization. And when I say rasterization, I'm going to say one thing that is super important for us to understand. The GPU of the PlayStation is a 2D rasterization engine, right? So the GPU only knows how to raster in 2 dimensions, right? So whenever we ask the GPU to render something, we only have X and Y positions on the screen. That is what it knows how to do. It rasterizes 2D objects. And the reason why I'm saying that, right? Keep that in mind, because this 2D rasterization limitation of the GPU is going to come back again and again in our explanation, right? This is one of the main limitations that actually gives a lot of those artifacts. That is why they are born, right? So remember, GPU is a 2D rasterization engine. Whenever we raster a triangle, whenever we raster a quad, those are going to be 2D triangles and 2D quads on screen space, right? In screen space. Right, and besides the CPU, VRAM, GPU, we have a couple of co-processors that are going to help the CPU, right? It's going to relieve a little bit of the processing of the CPU. For example, the CP0 is what we call system control, controls things like interrupts, events. So this is actually part of the kernel, right? The system control of the PlayStation. But the one that I'm really interested in this video is the coprocessor 2, which is called the GTE, or the Geometry Transformation Engine. This GTE coprocessor is the one responsible for 3D math, right? So vector transformations, matrix transformations, these things that are super important for 3D operations. The GTE can perform these things a lot faster than what the CPU could do. Right? The CPU is very capable, right? This RISC CPU has a pipeline, is very capable, but the GTE, it is designed, right? It is hardwired to perform these computations, these vector operations, rotation, projection, all those 3D math things. The GTE performs these things in a lot less clock cycles than the CPU. So GTE is going to be super important for our understanding. And then we have things like motion decoder and SPU for audio. We have CD subsystem. But what I'm really going to focus is the CPU, the RAM, the VRAM, the GPU as this rasterization engine, and the coprocessor, mostly the GT, right? So just keep in mind that this is what the PlayStation is packing, right? That is what we have inside our PlayStation box. Right, with that out of the way, let's talk about some of the graphics primitives that we have for the PlayStation, because everything that we draw with the PlayStation, right, before we talk about texture wobbliness, we need to understand what are the primitives, the things that we can draw and ask the GPU to draw in the PlayStation console. And these are the PlayStation drawing primitives that I'm calling, right? And these are actually primitives that are native to the PlayStation. It knows how to draw lines. We can draw sprites, which are basically these 2D reward images. I can have flat shaded polygons, and when I say flat shaded, it's basically just one solid color polygons, and that can be triangles or quads, right? So I'm showing a triangle right here, but it could be a quad with 4 vertices. And I can have also a Gora shaded polygon, and Gora shaded, it means that it is a triangle or a quad that has, for each vertex, I have a different color, and then the GPU knows how to interpolate those colors inside the triangle. So we have this blend inside, right? So interpolation of vertex colors, that is a Gora shaded polygon. And we also have a very famous textured polygon, which can be, again, a triangle or a quad, and it basically is going to give us, right, for this vertex, and this vertex, we're going to have special UV texture coordinates that are going to map to an original source texture in VRAM, and then the GPU knows how to go pixel by pixel, interpolating those UV coordinates, getting the correct color of the texture between this vertex UV, this vertex UV, and this vertex UV. All right, so this is what we call texture mapping, and this is one of the primitives that we can have for the PlayStation, a texture triangle or a texture quad, right? That in the case would have 4 vertices. And let me just open here a little bit of an explanation for us to understand what really goes on at hardware level, right? So the way that things work with the PlayStation is, the PlayStation has a CPU, right? As we know, this MIPS RISC CPU, super powerful, super interesting. The CPU cannot go and access directly VRAM, right? So the video RAM is what gives us that frame buffer, meaning the memory, the mirror in memory that contains the data that is being displayed on the monitor, right, on the CRT display. So VRAM, this chip VRAM that we have in the motherboard, which are actually 4 chips, right? So these 4 chips that are video RAM, inside video RAM, we are going to have the frame buffer, right? So it's going to be this mirror, this data that is going to tell us what is being displayed on the frame buffer. But this is the thing. The CPU does not have direct access to VRAM. So I cannot just say CPU and start sending instructions to fill VRAM frame buffer. The one chip that does that is the GPU. So the GPU is the machine that knows how to perform rasterization on VRAM on the frame buffer. So the only way that I can go and draw into the frame buffer and use VRAM is by issuing GPU commands. And let me just show you how this looks. I am going to start sending always to the GPU, right? The only way I can access VRAM is through the GPU. The CPU is going to start sending packets of information. So packets are going to be these 32-bit long values, right? Or what we call words in the PlayStation world, right? So these 32-bit word values, these are going to be a 32-bit number, 32-bit number, 32-bit number, 32-bit number in sequence. So these are the packets, these 32-bit values, one after the other. And these are going to be the packets that are going to tell the GPU what and where to draw things in the frame buffer, in VRAM, in video RAM. So let me just give you an example right here. So let's just say that the first packet that I'm sending, it is a 32-bit word, and this first byte right here, these 2 nibbles right here, this is going to be a value that dictates the type of primitive that I'm using. So for example, if I use the type of primitive 20, that is going to be a flat shaded polygon. So if I use 30, it's going to be a Gora shaded. So depending on the byte that I send right here, the GPU knows what type of primitive is going to draw. It is a line, it is a sprite, it is a flat shaded polygon, a Gora shaded, or a texture polygon. So this byte will tell the GPU what is the primitive that we're drawing. And then after that, I have a byte for blue, a byte for green, and a byte for red, which is, no surprise, going to give us the color of that flat shaded polygon that we want to draw. And look at the other packets that follow the first one. This next packet of 32 bits is going to be broken down into 16 and 16 bits. The first 16 bits is the y-coordinate of the first vertex, and then the next 16 bits is the x-coordinate of the first vertex, and then I have the next packet, the y and the x coordinates of the second vertex of the triangle, and then the y and x coordinates of the third vertex of the triangle. So I am specifying where in x and y coordinates I want that triangle to be drawn, rasterized by the GPU. And as the GPU receives these 32-bit packets, it knows how to go, and as we issue these packets and we send these things to the GPU is the one responsible for going and drawing into VRAM space. So the GPU goes and fills that frame buffer, rasterizing things in the frame buffer, and that is what we see in the display, right? So this is, again, this is a conversion to assembly, right? So this is MIPS assembly. This is how we usually send things, these packets, to the GPU. I can load register with the correct data, I can load immediate a register with the first packet, and then I store a word, right? So see, SW, store a word, store these 32-bit values from this register into the GP0 port, and then I load another packet with the x and y values, I store that word in the GP0, I load another immediate value, it's stored in GP0, I load another. So do you see, basically just loading and sending, storing values in the GP0 of the GPU, right? This is a GP0 port, which is mapped into this GPU. And of course, don't worry if you don't understand assembler, right? MIPS assembler, you don't have to. Just understand that what we're doing is basically just loading and storing, loading and storing, loading and storing these words, these 32-bit values, these packets that we are sending to the GPU. This is all we need to do to draw a flat shaded triangle in the PlayStation, right? But do you see that? At this point, everything is 2D. We are only asking the GPU to draw things in this 2D frame buffer. This is 2D x and y, 2D x and y, 2D x and y. So the question is, how do we go from 3D, because we have a 3D object with a 3D world, right? This conceptual 3D object and world in our minds, and all these OBJ files and these characters, right? The game player, the enemies, they are all 3D objects with vertices and points and triangles. How do we go from 3D into 2D? Well, whoever performs this projection from 3D to 2D is the GTE coprocessor, right? The coprocessor, the GTE, is the one moving things from 3D space into 2D screen space. Keep that in mind, because now I want to talk to you, right? Everything is going to come together and everything is going to end up here, into the wobbly textures, right? So why do PlayStation games wobble textures? The reason for that is, let's just go back and analyze again the fundamentals of what we call texture mapping. Texture mapping, whenever we are mapping textures, is basically the idea of having a source image. This can be a PNG file or a JPEG file. In our case, it's just a 2D image that is loaded into VRAM, so it's just a texture image like a PNG file or a JPEG file that we have to go and load into VRAM. Given that we have this flat image right here, and given that we have, let's say, our enemy or our main player or some 3D model that has vertices and faces and triangles, this is 3D, and then we have these points right here. Do you see these values? This is what we call UV coordinates. This vertex right here has UV coordinates 0.75, 0.55. So 0.75 in U, 0.55 in V. So it is right here in the original source texture. So we are mapping this vertex to this area right here, this UV coordinate of the original texture. And the same happens for this vertex, 0.40. So 0.40 is right here, and then 1.00, so 1.00 UV coordinate. We are mapping these vertices, these UV coordinates for each vertex to an original texture. The result is this thing right here. the first vertex is mapped to that UV coordinate, the second vertex is mapped to that second coordinate, and the third vertex mapped to that third coordinate. But given that we have all these values, we need to go and interpolate those three values to find what is the internal color that we have to paint this triangle. Do you see? So we have this UV coordinate, this UV coordinate, and this UV coordinate. But the GPU needs to go and interpolate, it needs to visit pixel by pixel of that triangle, and for each pixel it needs to go and compute. Okay, so this pixel right here, what is the source color that I have to go and pick from the original texture to paint this pixel? It goes, it interpolates those three values to find where in the color, in the texture, I have to go and paint. And then the next pixel goes, interpolates those three values and find the color. Next pixel. So you see, pixel per pixel. Rasterization stage has to go and interpolate those values. And right here is where the problem begins, because this interpolation, for us to interpolate these values, everything works well in 2D, but when you have 3D and depth and perspective being applied on those geometries, right? So if the triangle has perspective, has depth in it, for us to correctly map that texture using perspective, using depth, we need to know the original depth value of the vertices. Look, let me repeat that again, because this is one of the most important sentences of the whole video, right? If you want to correctly interpolate the values inside this triangle, considering perspective, considering that this triangle face is tilted using this depth value, for us to perform this correct interpolation, it can only be done if we know the original depth, the original z value of these vertices. And the PlayStation, the GPU, does not have access to the z value of the vertices, so we cannot perform what we call perspective correct interpolation. Do you want to make things clear? Let me just show this image right here. Think about that flat texture, right? So that is, let's say, a quad looking at us, right? Perfectly looking at us. That is a flat texture, everything is correctly mapped. This thing right here is what the PlayStation does, is what we call a fine texture mapping. And I think it's easier for you to understand. You see, it's almost like that wobbliness is already showing. Look at what happens. If you break that quad into two triangles, the interpolation that the PlayStation does is called affine, and it does not consider the depth of that geometry. So if you think about it, right, try to ignore the fact that this looks like a quad that has perspective applied. Think that this is just a geometry. This is just a triangle face, and the interpolation is done linearly, right? So do you see, we have these values, and that value, and all the interpolation that we have right here is done linearly across the face of the triangle, right? Think of it as this is just a 2D flat triangle geometry, and do you see how the interpolation is being done linear right here? You have all these straight lines that are linear, right? They do not respect depth or perspective. This is called linear interpolation, or what people will call in the PlayStation world affine texture mapping, which does not consider perspective, does not consider depth. And this happens also with this triangle. You see, everything is straight lines, linear interpolation, not considering the perspective. That is why you have almost this bend right here, you have this zigzag right here, which is what causes that wobbliness. Do you see how things, they kind of distort right here in the middle whenever these two triangles meet? This distortion right here is absolutely classic in PlayStation games, and as things move, you will see, surprise, surprise, wobbliness of textures. Right? So all this distortion, this affine texture distortion, because things are being mapped and interpolated linearly, that is why we have this distortion, this artifact of the textures, because we are doing things linearly, right? There is no perspective being applied. And in a perfect world, if we had perspective correct interpolation, so perspective correct texture mapping takes into account the perspective of those vertices. So this is almost like I have a quad that is being rotated inside the screen here on the right. So you can imagine that this is a quad in 3D. So this has a bigger depth value. This has a bigger depth value. So do you see how the texture respects the depth of the vertices, this is what we call perspective correct texture mapping. And this is something that the PlayStation cannot do by design. And the result, right, given that we have these two triangles, the result is that the texels of the texture that are being mapped right here, they respect the depth and they get smaller and distorted as the perspective increases and as the depth increases right here. And once again, we can only compute perspective correct interpolation if we have access to the original depth z value of the vertices. And this sentence right here explains why we cannot have perspective correct interpolation for the PlayStation. Because once we project things, we lose the z value. We have no z buffer in the PlayStation. So once we lose this z value of the original vertices, we cannot perform these things by design. We can only end up with affine texture mapping, which is this linear interpolation with these values. Actually, let me just rephrase one thing. Do you see how I say that we can only compute perspective correct interpolation if we have access to the original z depth value? That is not really technically true. What we need for the correct interpolation is what we call the reciprocal of z, which is 1 over z. But I think the idea holds true, right? We need the reciprocal of the z component, so we need 1 divided by the original z of those vertices to perform perspective correct interpolation. And just as a small parenthesis, I'm not going to go and expand the whole mathematical explanation and the derivation of why 1 over z is what we need instead of just z, right? We cover that in other courses, right? In our 3D graphics course, we actually go and we derive the mathematics of why is 1 over z. But just in very simple terms, it means that whenever we are interpolating values from the vertices, the z value is not linear. It doesn't interpolate linear across the screen. So the original z value cannot be interpolated linearly, but the reciprocal of z, so 1 divided by z, is linear across the screen. So the interpolation of 1 divided by z of this vertex, 1 divided by z of this vertex, and 1 divided by z, the interpolation of these reciprocals of z, that is linear across the screen face of the triangle, and that is why we can. But don't worry too much. I just wanted to keep in mind that the reason why we cannot have perspective correct interpolation is because we lose the z. And you know what? Let me just go even deeper because I want to show to you the actual code. So right here we have what we call the GTE. Remember the GTE, that coprocessor that helps us perform graphics math, right? Vector, matrices, and things like that. Look, one of the most important things that the GTE performs is we give a triangle to the GTE, and then the GTE knows how to perform rotation, translation, and perspective projection, right? And perspective projection is super important because is what converts things in this 3D conceptual world into screen space, into 2D, right? That is what projection means. So this rotation, translation, and perspective together, this is one thing that the GTE knows how to do natively, right? It is hardwired, right? By design, the GTE knows how to perform that in few clock cycles. So you don't, again, trust me, you don't need to understand MIPS assembler to understand what I'm telling you right here. You don't have to understand each one of these lines, but the high level, the big picture of that is, if we have a routine called rotation, translation, and perspective tree, what happens in the GTE is, the way that the GTE works is, we are going to store the vertex values of the triangle. So each one of those vertex 0, vertex 1, and vertex 2, we're going to store the vertex values x, y, and z into registers of the GTE, and then we're going to issue a command for the GTE, and the GTE does its magic and computes that perspective divide, the perspective projection, the rotation, the translation. It does everything, and then it stores in other registers the result, right? It spits out the result in other registers. Look at what is going on right here. These lines of code right here, if you want to break down, it means LWC2, so load a word into the coprocessor 2, and then we are storing the x and y of the first vertex, and then we are storing the z of the first vertex. So we are basically just loading registers of the GTE with the vertex x, y, and z that we need for the 3 vertices. Do you see? So here is where we are inputting the three local vertices x, y, and z for the GTE to perform. And then we can, this one right here, we are going to issue a command for the GTE to use these registers and perform rotation, translation, and perspective divide, right? Perspective projection. Whenever we, this is what we call RTPT, right? This very famous RTPT means rotation, translation, perspective of three vertices, right? Of triangles. As we issue this command, the GTE is going to do its magic and is going to then, we have in other register, we have to now go and store the result of what we want. So remember, we inputted in the registers of the GTE three vertices, V0, X, Y, and Z, V1 vertex X, Y, and Z, and V3 vertex X, Y, and Z. The RTPT command does its magic, computes the perspective, rotation, translation, and then we now have here the output of the GTE. Look at how the output of the GTE we are storing, right? SWC2. So I store a word coprocessor 2, right? SWC2. We are storing what I'm calling SXY0, XXY1, and XXY2. This output that the GTE spit out is three screen coordinates only with X and Y. And you probably already, if you have a sharp eye, you already understand that. We are inputting X, Y, and Z, and as soon as the RTPT command goes and performs the perspective projection, we are losing the Z component, and we only have this screen space values with X and Y, 2D values X and Y. And that has everything to do with the next issue, which I want to cover, which is the fact that the PS1 does not have what I call a per pixel Z buffer, right? So we don't have this buffer in memory with the Z component per pixel. We only really have the depth per primitive. And that gives us an artifact, which we call this primitive Z fighting. Sometimes triangles that shouldn't be in front of the others, they kind of go and they fight, and they have these artifacts where you have these triangles popping on top of each other. And to really understand that, I just want to now talk to you about how do we actually go and we sort and we order the drawing of the triangle. So how do I know which triangles should be drawn on top of the other? Because ultimately, we have to remember that we are sending packets, right? Those 32-bit packets to the GPU with information of the primitives that we want to display. But the order that we send those packets have to do with the order that we are going to actually draw those things. So which triangles are going to be drawn on the back and which triangles are going to be drawn in front of the others, right? So what is this Z ordering, right? It's almost like doing this painter's algorithm where we have to draw things in front of the others whenever they are closer to the camera. The sequence that they are going to be drawn has everything to do, right? The way that the SDK and the PS1 usually do things is using what we call an ordering table. So we use an ordering table, which is nothing more than a data structure that is going to go from back to front drawing things, right? So we're going to have this data structure in memory is going to be, if you want to know, it's a linked list, right? So we're going to have an ordering table, which is basically a linked list where every position we go and we put that primitive that we want in the order that we want them to be drawn, right? So as we have these primitives being added to the linked list, I can start adding the first primitive, and then I have a little pointer to the next, and then I have a second one. And if I have already another triangle, it can be here on this one, and then I can add here. So the order that I want to add those things, I have complete freedom to go and assemble this linked list the way that I want, with the order of primitives, with the way I want them to be drawn, right? In this case, I'm defining that they are going to be drawn like from back to front, let's say, right? This is the first one and these are the last ones. So I have an order of rendering, and that order of rendering is going to be basically my painter's algorithm, right? Because these primitives right here are going to be drawn on top of the previous one. So this is the order that I want to draw them. Whenever you are programming, you can actually decide if you want to go from back to front or from front to back. You can have this reversed list as well, but again, you have the freedom to create this ordering table the way that you want. The question is, how is that related to our primitive Z fighting? Well, think that the Z, the depth of where things are drawn on this ordering table, it is not the depth per pixel. we're going to have a depth, right? The position of each primitive in the ordering table has to do with the entire primitive. So this is an entire triangle, this is an entire quad, this is another entire triangle, so it is not a per pixel depth buffer. Everything is basically per primitive, meaning that each primitive has its own position in this ordering that we have to draw. So look at what happens. Look at this example right here that I'm going to show. This thing right here is the T-Rex demo that came with the PS1. Look at the legs of the T-Rex as they connect to the body. Do you see how we have some triangle popping back and forth? There we have that Z fighting between some of the triangles of the leg and some of the triangles of the belly. That is a classic example of this type of data structure where we have one depth value per primitive, right? So it is not a depth value per pixel. We cannot control the depth per pixel. It is one depth value per primitive. So we're going to have this popping of primitives that just show and appear in front of each other because we have to go and decide which one is rendered on top of the other. Do you see? Ordering tables, the depth value is per primitive. So each position of our linked list, of our ordering table, has to do with where those things are in this depth range, right? So how do we want to go and display these things from back to front, usually? And just to give you a spoiler already, right? This is something that we do in our course. How do we decide which position each primitive occupies in our ordering table? Well, you will be surprised to know that the GTE, right, that coprocessor, also can help us decide what is the position in the ordering table. So think about a primitive, and how do you decide where is the position in the ordering table that you have to go and insert, right, to go and sort that primitive, add that primitive in the ordering table. What you will usually do is, well, if you have a triangle, and each one of those vertices of the triangle, they have a Z value, you could get away with just averaging those three Z values, right? So the vertex 1 Z value, vertex 2 Z value, and vertex 3 Z value of the triangle, if you add those three Z values and you divide by 3, that will give us kind of like an average of that Z value. And that average is something that the GTE can, by design, compute. So it has certain registers you load, and you have a command, a special command that you issue to the GTE, and the GTE already gives you this average Z value, right? It works for triangles, it also works for quads. So the Z value, right, that position in the ordering table with this average Z value, the GTE spits out, and you can use that value to go and know what is the index, right? What is the position in the ordering table that you go and you add that primitive. So again, GTE to the rescue, right? GTE is super, super cool coprocessor. I really like the GTE and the way that it does things. It really helps the CPU to perform things a lot faster than if you didn't have the coprocessor. All right, so we just explained why we have all this triangle popping because of the depth value per primitive. I think it's time for us to move on and talk about another artifact, which is polygon jittering, right? So the polygons of the PlayStation, they jitter, right? They jump around. You will see that as characters move, as the player moves, you will see that, you see how the polygons kind of jump around? It doesn't have this smooth movement, right? Every time that you move the polygons, it's almost like they are jumping in this pixel grid. This jittering of polygons is very, very unique for the PlayStation era. And if you try to look for information about why these things are, if you go to forums or if you go to even blog posts, sometimes people will say that, look, the reason why the PlayStation have all these jumpy polygons and everything kind of snaps to the grid is because the PlayStation has no native floating point values. And I'm going to tell you right now that that is not really the reason, but they are not completely wrong, because the PlayStation really does not have native support for floating point numbers, right? So this is important. The PlayStation does not come natively with floating point number implementation, right? Numbers like 10.33, 7.456. We don't have this decimal point using floating point numbers. Because, let's be honest, right? Most modern games and modern computer, they have already support for what we call hardware floating point numbers, right? So if you have your processor, if you have the way that your processor is already hardwired, it does have support for this specification, this standard called floating point numbers. And we are basically used to work with floating point numbers in our games, right? If you have a player, if you want to talk about these vector quantities or these ideas like velocity, acceleration, force, wind, drag, damp, and even things like the angle of the direction of the player, right? If you're talking about radians, it is only natural that we have this fractional representation, this floating point numbers that says that the angle is 2.0944 radians, right? So we're talking about radians, degrees. It is usually useful to have floating point numbers. So it is no surprise that most of the time, if you are a modern programmer in a modern game engine, you're going to declare these values, right? The velocity x, the velocity y, the wind x and the wind y component, the angle of the direction of the player, everything is going to be a floating point number, right? Float, float, and float. And the representation that we usually use is what we call the IEEE 754, which is the standard that separates things into a sign bit right here on the far left, and then we have bits for the exponent of the number and then the mantissa of the number, which is basically, right, the number is given by this formula right here. So -1 raised to the sign of the number times 1 point the mantissa times 2 raised to the exponent -107. This is a very fancy and smart formula, so we can represent a lot of numbers and a lot of fractional part, right, all these decimal points. This is how we can basically optimize and represent a lot of these floating point numbers. So the IEEE 754 implementation is a smart way that engineers found to try to represent as many real numbers, in quotes, right? So as many real numbers as possible, only using 32 bits. It can be 32 bits, or if you use, instead of floats, double, then you can use 64 bits. But there is a limitation, right? You can represent a finite number of real numbers, which is almost like a paradox, but yes, we are trying to represent as many real numbers as we can using this smart representation. But again, this is not what the PlayStation uses. The PlayStation doesn't even know about the existence of these things right here. So Gustavo, if we don't have this, what can we use to represent these fractional numbers? All right, so how can games represent velocity? How can games represent the quantity of acceleration? All these things that could benefit from this fractional part, right, these decimal values. Well, that is where we have what we call fixed point representation. Look, the alternative, right, that's better suited for a system that does not have an FPU like the PlayStation, we don't have a floating point unit inside the processor, it is to use, then, the alternative is to use something called an integer-based fractional number system, commonly known as what we call fixed point representation. So what does fixed point really mean? Well, it means that instead of keeping a floating point value around our number, right, instead of having this little point that floats around our number, we're going to fix it. We're going to say, I'm going to reserve a fixed number of bits for the integer part, and I'm going to have a fixed number of bits for the fractional part of the number. So this example that I have right here, this is a 32-bit number where we are saying that the first 16 bits are the integer part of the number, and the remaining 16 bits on the right are going to be used for the fractional part of the number. So you see, integer bits, these bits to the left, the 16 bits right here, they're going to store the integer part, and then it's almost like we have a divisor right here, and then the least significant bits are going to represent the fractional part of that number. So we are not using actual floating point number standards, we are using a fixed point representation. And this is something super common in the PlayStation world. All right, so this is an example of a 16.16 representation. It doesn't have to be 16.16, so depending on the range of values that you want to represent, right, the magnitude and the range of integer values, or how much more precision you need for integer part, you can move this fixed point number around. So you can have, for example, a 20.12 fixed point representation where you reserve 12 bits for the fractional part and 20 bits right here, including the sign bit, 20 bits for the integer part. That means that you can represent a lot more integer values. If you want to increase the range of integer values that you want to represent, we can use this one right here. The resolution of decimal fractional values that you can have is 12 bits. All right, look, I know it's taking a lot of time for us to talk about polygon jittering, but trust me, we're going to get there. Because the question is, what do we use then with the PlayStation, right? So what type of fixed point representation, what is the resolution of integer and fractional that the PlayStation uses? Well, the answer is, it depends. Sometimes game will have a different representation for velocity, and then a different one for acceleration, a different one for angles. You can kind of pick, but that being said, remember the GTE? The GTE kind of has natively support for 20.12. So this is usually what the GTE will use. Usually the GTE will use 12 bits to represent the fractional part of a number, which means that this is what the GTE is going to use, and if you are programming for the PlayStation, this is usually what you're going to use as well, 20.12. Let's just analyze what that means for us in terms of numbers, right? If we have 12 bits for the fractional part, it means that 2 raised to the 12 is how many values we have to store the fractional part, right? So 2 raised to the 12, these many bits, we are going to have 4096. This is going to be our 1.0. Do you agree? So 4096, if we have 1,0,0,0,0,0,0,0,0,0,0,0, this is 4096 in fixed point representation, but it is trying to represent 1.0 in terms of actual number for us, right? The quantity 1.0. Does that make sense? So all these bits right here, they are only going to represent, they are going to be the granularity of the fractional part that we have. It doesn't matter what we have right here in these bits, they are not part of our whole number. They are just the fractional part of what we're trying to represent. And that is why, if I have 1 and then all zeros right here, these things right here with 0 and then just 1, that means 1.0. That is the number that we're trying to represent is 1.0. But if I have 0.00054, then it is a different set of bits that I have activated here. Let's just see if we can make things clearer. If we look at the code, right, if we translate this into C code, it is very customary that we're going to have a constant called, let's say, 1, and then for us, 1 is 4096. And then look at this. If I have a fixed number, right, and this is an integer, right, it's just a normal integer value. If I get my number and I add 4096, it means that I am incrementing by 1.0. Does that make sense? And if I subtract by 4096, I mean that I am subtracting by 1.0. And if by any chance I get my fixed point number and I add 2048, which is half of this 4096, it means that I'm adding half, or 0.5 to that number. And the same, if I am subtracting 6144, that means I'm subtracting 1.5 from that number. Do you see that everything has to do with this 12 bits that we can represent? This is the fractional part. Everything has what we call the scalar. This you will see whenever we talk about fixed point numbers, people talk about the scalar. The scalar means, what is this fractional 1 for you, right? So this is the scalar. The scalar for us is 12 bits. That is what represents 1.0 for us. And speaking of scalar, if you just look at this example, if I have a long, right, just an integer value long, a, and I initialize with 20 times 1, this is basically converting 20 to fixed point representation, right? I multiply by my scalar, my 4096, this is the number 20 for us, right? But it is encoded in fixed point manner. So it's basically almost like converting things to fixed point representation. So I convert 20 to fixed point. The same thing, if I have a different number and I want to convert 17 to fixed point number, I say 17 times 1, our scalar, that means I'm converting 17 to fixed point representation. And look at that. Long C is the result of A plus B. This is the beauty, right? Addition, even subtraction, it just works out of the box. Because if we have everything as integer values and we are just basically scaling things by the fractional part, right, our scalar right here, to add two fixed point numbers is as simple as just adding them as if we were adding two integers together. And that's exactly it. Of course, considering just paying attention to the overflow or the underflow, but it is basically just adding two integer values together. Addition just works. That's the good news. So addition of two fixed point numbers is as simple as adding both integers, and subtraction of two fixed point numbers is as simple as subtracting both integers. right? Multiplication and divisions, we have to just pay attention to the overflow, underflow, but again, it is as simple as considering this fractional part always, right? Whenever we are talking about a number, it is always the integer part and the fractional part. In this case, the GTE, right? Usually using 12 bits for the fractional part. Right, Gustavo, why are we talking so much about fixed point numbers? Because most people, most blogs and most people, they will tell you that the reason why polygons jitter is because of this lack of precision of not having floats. And I'm going to tell you that that is not the case, right? That is not the main reason why this polygon jittering are. So polygon jittering is not really just the result of lack of floating point numbers. Polygon jittering is a direct result of the PlayStation GPU not have what we call subpixel rasterization. What does subpixel rasterization mean? Well, subpixel rasterization means that whenever we are talking about the pixels that we are going to rasterize things, the pixels on the frame buffer, the GPU cannot interpret values in between the pixels. Everything is integer based. There is no subpixel accuracy in our movement, right? So think about this. Screen coordinates, whenever we have triangles or quads that they are moving around, rotating or moving, screen coordinates, those x and y coordinates of the GPU, they don't have fractional part and they are going to be rounded up or down to the integer values and they are going to snap to the pixel grid. Let me repeat that again. Screen coordinates are going to be rounded to integer values and are going to snap to the pixel grid. Everything is always going to be rounded to these integer values, and that is why we have polygon jittering, right? So think about this. Think that we have this simple raster right here of all these pixels. If our triangle rotates, it is not going to be a smooth rotation. Everything is going to jitter and snap to the grid, right, to this integer position. So we're going to have snap, 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 snap. Do you see? Everything is very discrete. All this movement snaps to the rounded integer of the pixels. There is no smooth between the pixels. And that is exactly what the PlayStation rasterizer does, right? The GPU can only interpret things at these integer values. There is no subpixel precision in the rasterizer of the GPU of the PlayStation 1, right? The OG PlayStation does not have subpixel accuracy. So let's just try to understand something. What does it mean to have subpixel accuracy? Which, again, this is not what the PlayStation does, right? The PlayStation does not do this. But if you were going to represent and have subpixel accuracy for our rasterizer, you are going to basically divide your pixels using fixed point representation, right? Using this fixed point number representation. It's almost like you divide your whole pixel into smaller subgranular parts. So this one right here is going to be one entire pixel, but for one entire pixel, you can have this internal movement values inside, right? Using the granularity, the resolution of a fixed point representation. And of course, the more bits for the fractional part you have, the more resolution you're going to have inside a pixel, right? But in our case, let's just say that I have 8 by 8 here. This is what we can have with a subpixel rasterizer. We can take advantage of all these small internal pixel values, and then as things move, as the vertex moves inside, we don't snap pixel and then pixel and then pixel. We can move inside these small granular parts right here. Does that make sense? And just to give an example of how these things are going to affect the look of our game, right? So things are not going to jitter as much. Look at this example. Let's just say that I have one vertex that is right here inside this pixel, and the next vertex of our triangle is, do you see where that magenta line is? Let's just say that that vertex is internally, right? Subpixel accuracy, so it's right there. As we have this line connecting these numbers, the rasterizer is going to look at each one of where this line visits, trying to paint the correct pixel, right? Rasterize that triangle, paint the correct pixel for that line. So this is what happens. If we were talking about the PlayStation, everything is just going to jump and jump and jump and jump, right? Snap to the grid, to these integer values. But if we're talking about a subpixel rasterizer, this is what we would expect. I would have as I move down, do you see? I move down internally inside the pixel. Do you see how the rasterizers changes? So it's almost like this smoother curve. And as I keep going down, 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 down internally inside the pixel, do you see? I move this one right here. So it's almost like it's a smoother rasterization effect than if we didn't have subpixel. Right? So again, this thing that you're seeing right here, right? This moving down, 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 down. This is not what the, yeah, you see, this is not what the PlayStation does. This is what we are lacking on the PlayStation. So that polygon jitter that we see is a direct result of lack of subpixel rasterization from the PlayStation perspective, right? The hardware of the PlayStation has a limitation that does not allow for subpixel accuracy in the rasterization stage. Whew, do you see everything that we had to review just to explain why textures wobble and why we have polygon jitter? There's a lot of fundamental ideas that are super important for us to understand, right? As programmers, as technical people, right? People that kind of are interested in computers, it is important for us to understand why these things are the way that they are. All right, so let's just quickly cover the last artifacts that I think are also very unique to PlayStation programmers. The next one is what we call, and what I'm calling, T-junction gaps. Look, whenever we are actually, in our PlayStation programming course, we created this kind of wipeout clone, right? So do you see these details right here? These gaps that sometimes in the junctions of the objects we see? This is just one example that we could see in our project, but look, this is visible in many commercial games for the PlayStation, right? So look at this example right here. Do you see those polygon gaps that appear every once in a while? Those are classic T-junction artifacts. And for us to understand why these things happen, I want to look, let's just take an example of our project right here, right? Whenever we have what I'm calling this T-junction artifact, let's just look at what we did in our project so we understand why this T-junction, what are T-junctions in the first place, but why they happen. So remember, right, if you took our course, we have a track, and that track is a 3D object, right? So we have to go and load that track. But depending on the distance of the track segments that we have, right, the track segments that are really far away from us, we just keep them as big, larger objects, and we don't want anything. But as we get closer, do you see, as we are, let's say that the player is right here, as we get closer to the camera, I'm going to start to subdivide the track sections. So I almost like have this level of detail, right? So the bigger is the Z value of the track section, I just don't subdivide. And if I have right here in this middle part, I'm going to subdivide once, those squads, and right here, as I'm really close to the camera, I'm going to subdivide 2 times. So I have smaller and smaller segments. And one of the reasons why we have T-junctions is because of this subdivision. This subdivision helps us achieve several things. First, remember texture wobbliness? Texture wobbliness, if we start dividing things and the geometry starts getting smaller and smaller, we cannot see that much, it's not that strong, the distortion of the texture. So this is one benefit of subdividing things. But as we subdivide and subdivide, look at this thing right here. Do you see these areas right here? This is what I'm calling T-junction. This is a T-junction, T-junction, right here as well, T-junction. So do you see how as we have this change in the level of detail, right, as we go from 1 to 2 subdivisions, we have T-junctions. As we go from 2 subdivisions to 1 subdivision to 2 subdivisions, we have more T-junctions. These T-junctions, why is that a problem? Well, depending on how we choose to tessellate our mesh, we might create these T-junctions between polygons. And here's the thing, right? Due to precision issues, again, precision issues due to lack of floating point numbers as we move, precision issues due to the lack of rasterization, subpixel, but lack of floating points, right? That accuracy issue that we have with fixed point numbers. Due to precision issues of our numbers, these T-junctions, they can cause gaps, or sometimes people are going to call them the seams, right? The seams between the polygons, in between our primitives. In this case, our quads, it can be the triangles, you get the idea. So as we have these T-junctions appearing as we change the level of detail, let's look at this very simple example. As we have these 2 triangles, one after the other, This example right here shows a perfectly connected triangle where they share vertices, right? So do you see how that vertex and this vertex right here, they are basically the same two vertices for both triangles. So whenever the rasterizer is going and painting that line is not going to cause any gaps, because as we are drawing that line of the first triangle, it's going to be the same line as we rasterize. The rasterization rules are going to follow the same rule, is going to rasterize the same pixels. The problem is that if we have now a T-junction in our geometry, that line right there, that vertex, might have a precision issue, and we end up going maybe a little bit left or to the right of that line. So it might be that with that precision issue of where that vertex is, we might have this T-junction, and we're going to have a little gap of where the position of that vertex is. Given that that vertex is not in the same line as those two other vertices, we might have a gap, and then the rasterizer will leave a little gap between those things. Because this vertex right here that is on that T-junction, given precision errors, it might not be lying on the same position as that line that we had between the previous two vertices, right? So there you go. Before we had two vertices that shared, those triangles, they were sharing two vertices, that was fine. They were always follow the same rasterization rule. These vertex right here might follow a different rasterization rule, and we might have a little gap. T-junction gaps. And that's why we see many, many games. Look at that. You have all these gaps sometimes appearing. You have all this, what we call sparks, right? You have all these little gaps, sparks appearing around. That is, again, a very, very common artifact from PlayStation games. T-junction artifacts. And we cover that a lot, right? In our game, as you saw, as we were programming, we actually saw, as we were changing the level of details from one division to two subdivisions and then 4 subdivisions, that is one of the reasons why we had that, right? Very cool. So what I want to cover right now is the fact that the last one that I'm going to cover is what I call lack of mipmapping, right? So look, lack of mipmapping is one artifact that PlayStation games bring, and it's basically the idea that whenever we are talking about textures, the way that we talk about textures and anti-aliasing of pixel values, we usually divide the textures, and it is customary that we have mipmapping. We have these different resolutions of textures, right? So we might have the original texture, which is this one right here. Let's just say that it is 128 by 128, and we can use this one, right, this high resolution one, for those track segments or those polygons that are very close to the camera. And as we get far away from the camera, we might decide to use a different resolution texture, right, for the track segments that are kind of divided just once. And then if we are talking about really, really far away polygons and triangles that we want to raster, we can use these very small resolution alternatives right here. So mipmapping usually means that we're going to have all these different resolutions, which is customary that we have these powers of 2, right? We have 16 by 16, 32 by 32, 64 by 64, 128. So these powers of 2 are very common when we talk about mipmapping. The PlayStation really doesn't have that, so we have these artifacts in terms of anti-aliasing, the way that things appear. We have all these artifacts in terms of texture visibility. And just to give you an example, the game that we were trying to implement, right, that wipeout clone, that fake wipeout clone, the way that they decided to do that is they kind of emulate, and they do use different texture resolutions. You have a higher resolution, a mid resolution, and a low resolution texture for each one of those quads of the track. So depending on where you are on the track tiles that are very close to you are using one resolution of texture, and then the textures that are a little bit farther away in this middle section are using a lower resolution, and then the track sections that are really far away, they use a very small resolution texture. They are basically the same texture, just different resolutions of texture tiles for each one of these track sections. Right? So this is how the Wipeout original developers decided to implement this kind of mipmapping idea, but just using different resolutions, right? The quality and the resolution of that image is different depending on the distance that we are from the camera. And that is super, super cool. Oh, and one thing that I forgot. Remember how we were speaking about the subdivisions of quads or triangles? Speaking of quads and triangles, it is important to mention that, yes, we can have quads or triangle primitives for the GPU, but internally, It doesn't matter if you're using a quad, internally the GPU will break that quad into two triangles. So in the rasterization internal phase of the GPU, it will basically process triangles, regardless if you're using quads or not, right? So just keep that in mind. So I think that concludes kind of the main aspects of the PlayStation programming, but most importantly, the reason why these things exist, right? And the reason why I decided to just create another video, right, another YouTube video that talks about PlayStation graphics is because I wanted to give a different perspective. And especially because things were very warm in my mind because I had just concluded the PlayStation programming course here at the school. It was super fun to develop this course, right? All these lectures, we really go and we learn how to program games for the PlayStation, right? The OG PlayStation, the original PlayStation. And yeah, you can, if you want to learn more about how the PlayStation programming works, all these details, right? Learn a little bit about assembler programming, learn all the tricks, optimizations, details of graphics, audio, how to move data around, how to represent values, variables. We talk about assembly, we talk about also using the C programming language, because the PlayStation is one of the first consoles, right? The first generation of consoles that it is not really mandatory that we use assembly programming. We are really starting to see more of an use of a higher level programming language like C, right? So we can use the C and the official Sony C SDK and libraries to program for the PlayStation. And this whole discussion that we had about graphics, right? All these artifacts, all this cool stuff that goes behind the graphics and the reason why graphics on the PlayStation, they behave the way that they do. This is just the tip of the iceberg of everything that we cover in our PlayStation programming course, right? So it kind of goes without saying, if you want to learn more, just go visit picma.com and you will see me there teaching you how to program PlayStation games. All right, so look, I think that's it. As always, thank you so much for the trust. I know that to get people's attention nowadays is super hard. And if you got to the end of this video, kudos to you, right? It's no small achievement. So hopefully I will see you at picma.com. Thank you very much for staying. See you later.